Welcome to the lecture 15 of the course Modeling and Ticket Simulation of Solar Photovoltaic Cell. Myself Mukul Kumar Das from Electronics Engineering Department, IIT ISM Dhanbad. In this lecture we will solve some numerical problems on illuminated semiconductor. In the last class we have discussed carrier generation in illuminated PN junction, carrier distribution and band diagram in a PN junction for forward bias and for illumination separately. Also we have discussed the position of quasi-Fermi level, how to draw the quasi-Fermi levels in illuminated semiconductor and illuminated PN junction and also in forward biased PN junction. In this lecture, we will be solving some numerical problems on carrier concentration of the photo-generated carrier in a illuminated semiconductor, extrinsic semiconductor particularly, and also we will show you by numerical calculation the position of quasi-Fermi level, how these Fermi levels are splitted in case of semiconductor under illumination. So let us first discuss on problem. This is the problem 4. So this is continuation of number is the continuation of our earlier problems discussed. That's why problem 4 I have mentioned here. So in 10th lecture we have discussed up to problem 3. And in first week tutorial, whatever the problem we have discussed, that is not numbered. So you can put it as a problem 0. So the problem is, consider a p-type silicon sample with Na is 10 to the power 15 per centimeter cube. Which is illuminated by a steady state light of intensity 336 milliwatt per meter square at a particular wavelength with photon energy say 2.1 electron volt. If the absorption coefficient of silicon at that wavelength is 10 to the power 4 centimeter inverse, calculate the number of EHPs generated per centimeter cube per second. Consider 100% efficient photogeneration. Consider exponential decay in light power. Also calculate the generation rate same at a distance of 2 micron from the incident plane. There is the same generation rate you have to calculate if you consider there is a exponential decay in the light power. So to proceed this problem, for the solution, let us understand the problem. You see the steady state light intensity is given and this alpha is also given. We have discussed in the last class that the generation rate, that is number of electron hole pairs generated per second per volume, that is related to the intensity and absorption coefficient alpha. So let us start with that. So first of all, let us calculate the number of photons incident per area and then we will proceed. So number of photon incident per area per second is equal to intensity I by h nu, where h nu is the photon energy at a particular wavelength, the wavelength which is considered here. So I here it is milliwatt per meter square. So this is say watt per meter square. Watt means, and in denominator this is 1 by say joule. So this unit if you consider, so joule per second, what is joule per second into meter square into 1 by joule. So joule cancel out, so per area per second. So this gives you per meter square per second. There is a number of photon. So similarly, if we write the number of photon per centimeter cube, we can also calculate. Generation of EHP per volume per second, that will be then alpha into I by h nu. Alpha is centimeter inverse or meter inverse, and I is here watt per meter square. So ultimately this product gives you per meter cube, that is per volume, and divided by h nu, that is single photon energy is h nu. So number of photons you have to calculate the total energy divided by single photon energy, because this watt consists of energy joule per second. Now question is, h nu generally is given in electron volt. So be careful, you have to convert this electron volt to joule when you divide this thing. So you can get this alpha I by h nu in EV into 1.6 into 10 to the power minus 19. And this number of photon will generate similar number of electron hole pairs because there is a 100% efficiency. So this will be nothing but number of EHPs generated per volume per second. So by putting the values, you can get alpha 10 to the power 4 centimeter inverse. You have to convert it to meter inverse. So 10 to the power 6 meter inverse. Intensity, this is milliwatt per meter square. So 336 into 10 to the power minus 3 by h nu electron volt is 2.1 into 1.6 into 10 to the power minus 19. That is, unit means this, you say joule per second. So number per meter cube per second. This is the concept, this number. That is equal to 2.1 into 1.6. If you multiply, you can get 336. So that's why this number is chosen in such a way that it will be easy to calculate. So 336 2.1 into 1.6, this will be 3.36. So this becomes 100, and 10 to the power plus 6 minus 3, that is 10 to the power 3 plus 2, 10 to the power 5, 10 to the power 5 and 10 to the power minus 19, so 10 to the power 19 plus 5, 10 to the power 24 per meter cube per second. So if you like to calculate per centimeter cube, you can also calculate. That will be by dividing 10 to the power 6, 10 to the power 18 per centimeter cube per second. Sometimes it is mentioned not in terms of per second. Sometimes it is per microsecond. So that is also required, because we will show you in the next problem this generation rate, that is G optical. This is denoted as G optical. This need to be multiplied with a average carrier recombination lifetime. That is generally given in microsecond. So if your GOP, that is optical generation rate, is per volume per microsecond, if you directly multiply with the microsecond number, that will give you the number of EHPs per volume only. That's why sometimes it is represented in microsecond inverse. So this can be written as microsecond means 10 to the power minus 6 second. So per second, so this is in denominator. So you have to divide this by 10 to the power 6. So 10 to the power 12 centimeter to the power minus 3 microsecond inverse, because 10 to the power 6 microsecond is equal to 1 second. In the next case, consider exponential decay in light power. You have to calculate the same at a distance of 2 micron from the incident plane. So it should be mentioned here that in this problem we have not considered any exponential decay. We have considered I, the incident intensity, that is uniformly illuminated everywhere. We are assuming no decay with the position. That is the assumption here. So in the next problem, next part of this problem, we have to consider that. So let us, for the second part, you consider that this is the P silicon bar. So light is illuminated from this side. This position is equal to 0. This position, say x is equal to L, length. You have to calculate the generation rate G optical at a point x is equal to 2 micron, no? Yes, 2 micron. Here G optical, how much? The only difference is G optical, it will be alpha I 0 e to the power minus alpha into D. Here D is equal to say 2 micron. I0 is the incident, that is 336 milliwatt per meter square by h nu. The same procedure, only additional term e to the power minus alpha d will be appearing. The same way you calculate that the last problem, that 10 to the power 12 per centimeter cube per microsecond or 10 to the power 8 per centimeter cube per second. If we consider 10 to the power 18 per centimeter cube per second into exponential minus 10 to the power 6 alpha value inverse into 10 to the power minus 6, because 2 micron into so you can calculate this easily, and it will be, after calculation, it will be coming 1.3, slightly less, you see, into 10 to the power 11 per centimeter cube per microsecond inverse. Earlier it was 10 to the power 12, 1 into 10 to the power 12. So here it is coming 1.3 10 to the power 11. So slight less. So intensity gradually decreases. So general formula of intensity, that I at any position x, Ix can be written as I0 e to the power minus alpha x. So second part of the problem also can be calculated in this way. This bracket should be given here. The next problem, that is problem 5. Here we will be calculating the position of quasi-Fermi level also. The same problem, just like before, a p-type silicon sample with acceptor concentration 10 to the power 15 per centimeter cube is illuminated by a steady state light, thus creating an optical generation rate 10 to the power 12 EHP per centimeter cube microsecond. Assume 100% ionization and no trapping, and tau n is equal to tau p is equal to 5 microsecond. Determine the electron and hole concentration n and p respectively, and the percentage change from their equilibrium concentrations. Here you have to calculate the generation concentration of electron and hole after generation, after illumination, and also you have to calculate the percentage change. Number B is check whether the magnitude of the product NP is greater than square of intrinsic carrier concentration or not. That we have to check. Determine the locations of the quasi-Fermi levels, IM, REFs. Actually, these quasi-Fermi levels, from the reverse side, if you see Fermi if you spell in from right to left, it looks like a FERMI, that is IMREF. Actually, this is reverse of Fermi. IMREFs, that is EFN and EFP. So this is nothing but indication of quasi-Fermi level. So from the right side it is Fermi, FERMI is Fermi. So this position of EFN and EFP we have to calculate. So first problem, first of all, this 10 to the power 12 EHP per centimeter cube microsecond, this is nothing but this microsecond is in the denominator. So EHP is nothing but 10 to the power 5 10 to the power 12. Centimeter to the power minus 3 microsecond inverse. In this way also you can write. It is better to understand. First of all, Na is equal to acceptor concentration 10 to the power 15. 100% ionization is there. That means the whole concentration, also the equilibrium whole concentration, be careful, equilibrium whole concentration will be P0 is equal to 10 to the power 15, the same. Now N0, the equilibrium electron concentration can be obtained from the mass equation, mass law, that is Ni square divided by P0. If you put the value Ni, that is 1.5 into 10 to the power 10. So this Ni is, if it is given, then you have to consider that value. Otherwise 1.5 10 to the power 10 you can consider. Generally this value will be provided to you in the problem. And in that case, Ni you have to consider Ni value is equal to 1.5 into 10 to the power 10 per centimeter cube. This is suppose given. This will be the equilibrium electron concentration N0. Now EHP is there. So delta N and delta P, they are equal. Why? Because there are no trapping. If trapping is there, that would be a different value in delta N and delta P. That means the number of electrons, extra electrons generated, that will be equal to number of extra holes generated. And tau N and tau P, both are same. Average carrier lifetime for electrons and average carrier lifetime for holes, both are 5 microseconds. In the last class, whatever we formula derived, that delta N, that is nothing but G optical into tau N, or delta P is equal to G optical tau P. But here tau N and tau P are same, so obviously they will become same. If you put this value G optical into tau N, that will be 5 into 10 to the power 12 per centimeter cube. I told you that per microsecond, the advantage of expressing G optical in per microsecond, if you multiply with the 5 microsecond, 5 only, so this gives directly the result. That's why it is given. So this amount of electron hole pairs, that is this amount of electrons and this amount of holes are generated per centimeter cube volume. Not here per second, this is total volume, in a total volume. So per volume, 1 centimeter cube volume if you take, you will get 5 into 10 to the power 12 extra electrons and 5 10 to the power 12 extra holes. So these delta N and delta P will be added to the equilibrium value. So P, that is the whole concentration after generation, that will be P0 plus delta P. Delta P is 5 10 to the power 12 and original P0 value, that is 10 to the power 15. So if you add 5 10 to the power 12 with 10 to the power 15, so significant change in the 10 to the power 15 value is there. That means there will be no significant change in carrier concentration of holes in a p-type silicon semiconductor when it is illuminated. The percentage change in the concentration for hole will be negligible. But what about delta N? Delta N is this 5 into 10 to the power 12. What was the original value of N0? N0 was 2.25 into 10 to the power 5. So N0 initially, so N0 plus delta N, if you do the calculation, that is equal to N. This is 2.25 into 10 to the power 5 plus 5, delta N is 5 into 10 to the power 12. See, huge change. Sorry, this is not 15, this is 5. This is value of n. So what is the percentage change n? This can be almost equal to 5 10 to the power 12. So this is almost equal to 5 into 10 to the power 12. So 5 10 to the power 12 after illumination minus earlier 2.25 into 10 to the power 5 delta, this is the delta n, change in delta n0 divided by the original value 2.25 10 to the power 5 into 100. This gives you the percentage change, and this percentage change will be coming 2.25 into 10 to the power 9%. So it is very high value in percentage. It may be, you may think that this is a high value. Actually, you see, original value is in the range of 10 to the power 5 and change value is 10 to the power 12. So in percentage calculation, as per theory, we are calculating in this way. So dividing the original value. So that's why it is coming very high. So this percentage change. But percentage change in the whole concentration, that is almost zero, because we have seen that P0 plus delta P, that will be nothing but almost equal to P0. So this is the solution of part A. Percentage change from their equilibrium concentration. Now second part, so check whether the magnitude of the product of NP is greater than square of intrinsic carrier concentration or not. This is very important. N and P. What is the value of NP? You know, N into P is equal to N0 plus delta N, P0 plus delta P. N0 plus delta N value we have obtained 5 into 10 to the power 12. P0 plus delta P is nothing but original P0. There is no significant change in delta P. So this 10 to the power 15. If you take the product, it will be square 10 to the centimeter to the power minus 6. So 5 into 10 to the power 27 centimeter to the power minus 6, which is must be greater than Ni square, much greater than, because Ni square is 2.25 into 10 to the power 20 per centimeter cube if you consider 1.5 into 10 to the power 10 per centimeter cube. Product N and P much greater than Ni square. That means this system is no more in the equilibrium, because at equilibrium we know Np, product of N and P always Ni square. But here product of N and P more than Ni square. So this system is no longer in a equilibrium. For equilibrium, N0, P0, Ni square, N0, P0 means equilibrium value, that's why 0 is there. So N and P product would be, if Ni square, then it would be also in equilibrium. But this is obviously not equilibrium. So illuminated semiconductor is not an equilibrium. Np naught is equal to Ni square, much greater than Ni square. Thus equilibrium is deviated. This is the second part of the problem is there. Now for the problem part C, so that is location of quasi-Fermi level, EFN and EFP. You know that equilibrium, at equilibrium, this is the Fermi Q into phi f, that is Fermi potential phi f into Q, that is KT ln P0 by Ni. If you put the values, this is the P0 value and this is Ni, so it will be coming 0.289 electron volt. Now, in presence of excess carriers, means in presence of illumination, when some extra carriers are generated, the position of the electron Fermi level and whole Fermi level will be different. So let us first, here I show you that is a equilibrium. So this Fermi level is equilibrium Fermi level. This is closer to the valence band because it is a p-type semiconductor, and if it is EI, that is intrinsic Fermi levels, it is at the middle. So this amount is nothing but Q into phi f. The single Fermi level here. But now illuminated case, the formula, that is EFN minus EI will be KT ln n by Ni. This n is, what is this n? This n is nothing but N0 plus delta n, this value. So N0 plus delta n we know that is 10 to the power 12, 5 into 10 to the power 12 divided by the Ni, this gives you 0.151 electron volt. So EI, that is EFN minus EI. That means EFN is above EI. This is a positive value. And the other formula, that is EI minus EFP, Fermi level, quasi-Fermi level for hole, that is KT ln P0 by Ni. If you put the value of P0, the same value, there is almost 2.289 will be coming, because this P0 will be nothing but equal to P0 plus delta P, that is almost equal to nothing but P0, that is P. In actual formula this is P, but since P is equal to P0 plus delta P is equal to P0, so you can write here and P0 by Ni, so this will be ultimately 0.289 electron volt. So same like a equilibrium Fermi level. If you take the decimal point, more decimal point, slight different may be obtained. That means the quasi-Fermi level for hole is almost at the same position of the equilibrium Fermi level. So it looks like this under illumination, after illumination, this is suppose EC and EV, this is EI, EFN is above EI, amount 1.151 electron volt. And EFP almost equal to EF. Earlier EF closer to the valence band, this is also same. Which indicates these two lines is a quasi-Fermi level, this one and this one. These are the quasi-Fermi levels. These are the positions. Another formula, if you see, that is difference between EFN and EFP, this difference, this gives you the product of NP. How? Because this Ni square into exponential EFN minus EFP, this difference between two quasi-Fermi levels divided by KT, this gives you the amount of product NP. Ni square into some factor. Into some factor there is exponential this factor. So if we put this value, ultimately EFN minus EFP is 0.44 because it is at 0.151 is 0.289. So the difference EI plus 1.51 above and EI minus this below. So these are the addition of 2.151 plus 289. This gives you the 0.44. 0.151 plus 0.289, this is equal to 0.44 electron volt. To put this value, product of NP will be coming this. So which is extra than Ni square by this amount. that is nothing but 5 into 10 to the power 27, which is much greater than the value of Ni square. Not only the same product value we have obtained in part B, the same value. So product of this NP after generation can be obtained by using this formula if you know the position of the quasi-Fermi level, and if you don't know, then individually delta and delta P you can calculate, and from that you can determine. So these two problems I hope has given you an insight how the quasi-Fermi levels are changing due to illumination. And also another thing, the change in the carrier concentration in minority carrier concentration is much more significant than change in majority carrier concentration compared to its equilibrium value. So we discussed two problems mainly on carrier concentration of photogenerated carrier in an illuminated semiconductor, and we have seen that increment of minority carrier concentration is more significant compared to its equilibrium value than the change in majority carrier concentration with respect to its equilibrium value. Second thing, quasi-Fermi level, the splitting of Fermi level due to illumination is there, and quasi-Fermi level corresponds to the majority carrier, that will not change significantly, but quasi-Fermi level for minority carrier changes significantly. Another thing we have seen, due to position, intensity of light decreases exponentially, but their decrement is not so significant. It depends on value of alpha, obviously, because it is multiplied with a factor e to the power minus alpha x. This is the reference book. Thank you.